Okay, so welcome to Math 140 Calculus 2. This is lecture 11. So what we're going to be doing today is we're going to be doing, for the most part, use substitution. So this is one of the big techniques of integration. There are a couple of ones that you just have to learn, you have to master. Use substitution is one of them. Partial fractions, it's good to know, it's a pain to use. And again, this is the 21st century. There are now plenty of programs online that will just do the integrations for you. But it is extremely valuable to have some sense and some ability to just look at things and see what they are. So I am a huge fan of Rubik's Cubes. We will have Rubik's Cube events later in the semester. Sometimes it's hard to disguise what you're doing. If I give you something in spherical coordinates, what do you think spherical coordinates deals with? Sphere, right. So in multivariable calculus, it's really not that hard to figure out when you use spherical coordinates, if you have anything involving a sphere. This is a Rubik's Cube of sort of the shear. Okay, so hopefully you can see this pretty well. This is a Rubik's Cube. Is this a standard Rubik's Cube? Or is it a little bit different than a normal Rubik's Cube? It's a little bit different. It's the same algorithm. What is the main difference? It's more than just numbers. It depends on how good your vision is. You can actually tell what's special about these numbers. Well, it's more than just they're the same. Let me see if I can zoom in enough so you could actually see. Can you notice anything about these numbers? Just at this angle, I think you can see something about them.
Oh, they're raised.
They're raised.
Like people who are blind.
This is for people who are blind. If you are blind, how would you do a Rubik's Cube? You can't do it by color. So this is to actually do it by, by braille and just fingering what's going on. It's not that hard to hide that this is really the same as a regular 3x3 cube. You don't need to feel it with braille. You can still just look at it. This cube over here is actually, I think, my favorite Rubik's Cube for the ease of solving versus the difficulty that it looks like. How many sides does a normal cube have? This has 12. So what you can do is you can pull this as, oh, you only do 6-sided cubes. Oh, I'm sorry. This is actually the same as a 2x2x2 cube. It looks very different. It's got 12 sides. It's really the same as a 2x2x2 cube. And I just flew one of my colleagues with that earlier this morning as a test. I am doing this to drive home the point of why are you taking this class right now? There's computer packages that do all this stuff. If you can convert it to the point where the computer understands what you're doing. And a lot of times, the real work is to do the algebra to reduce it to something that we recognize and then can apply existing techniques to. And that's the real emphasis of much of this semester. How do we look at things so that we can then recognize what to do so that we know what to try next? And I've already talked about the crying baby. Yes, you just go through things one after the other after the other. So I had given people a quick few moments in case anybody was having trouble zooming in to call in. Okay. So I want to talk about two methods of integration. The first, my students and I decided to call it the bring it over method. I'm not sure if anybody has ever named it. I wouldn't be surprised, but we like calling it the bring it over. And then the second is the main point of today, use substitution. And I just went online and I searched for use substitution and huge number of problems and write-ups up here, and we'll just work through a couple. The more you do, the more comfortable and confident you become. So let's talk about the bring it over method. So here we have the following integral, e to the cx times cosine x dx. Does anybody have any thoughts about how we might want to integrate this? This is not a function where I recognize the antiderivative. What could we try? By parts, we've really done nothing else. So if we're going to do it by parts, we need a u and we need a dv. you've got essentially a 50-50 chance. I could make one of them equal to 1, but what a line if that counts as the phone going home. It's borderline. It's borderline. Okay. What do you want to be you? So I'll put you on the hot spot to get out of it. What would you choose for you? Okay, so you will choose u to be cosine of x, and then dv would be e to the cx dx. So what would du equal? So if u is cosine, what's the root of cosine? Negative sine, so it's negative sine of x dx, and v, so what function has derivative e to the cx? Good, 1 over c e to the cx. And I'm using that this is going to be uv at 0 pi minus the integral from 0 to pi of v du. So let's just substitute in. So I is going to be uv, so it's going to be 1 over c cosine x times e to the cx at 0 and pi minus, and I have a minus becomes a plus, the integral from 0 to pi 1 over c, I can move the 1 over c outside. And I'll have sine of x times e to the x dx. Okay, so I've got cosine x e to the cx. When x equals pi, what's cosine x? Negative 1. So we get negative e to the c pi over c. And now, when x equals 0, what's cosine of 0? 1. So it would then be minus e to the 0, which is 1, so just minus 1 over c. Plus 1 over c, the integral from 0 to pi, sine of x e to the x dx. Don't know what that integral is. What could I use to try to figure out that integral? Let's do integration by parts. And so this is where we're normally careless and we'll say, let's let u and dv and just use those always as our dummy variables for this. What would you want u to be? And what would you want dv to be? All right, so let's take u to be sine of x. dv is going to be, and this should be e to the cx. Drop to BC. And then dv would be e to the cx dx. So what would du equal? So it'd be cosine of x almost dx. And what would v be? Good. 1 over c e to the cx. That's exactly what we had before. And so putting this together, we have I is equal to negative e to the c pi plus 1 over c plus 1 over c. And now we do the uv. So we're going to have 1 over c sine of x e to the cx at 0 and pi minus the integral from 0 to pi. We have a 1 over c cosine x e to the cx dx. Okay. Well, what's the sign of pi? 0. What's the sign of 0? Also 0. So the boundary term vanishes. So we get I is equal to negative e to the c pi plus 1 over c plus, sorry, it's minus 1 over c squared. What's the integral from 0 to pi of cosine x e to the cx dx? Yes! What's its name? We gave it a name. Sorry. Well, look at it. It's named on the first on the top of the slide. What are we calling the interval? I. So I is equal to negative e to the c pi plus 1 over c minus 1 over c squared I. How do we solve for I? You get I on both sides. On one side, so take the minus 1 over c squared I and bring it over, and then this becomes 1 plus 1 over c squared I equals negative e to the c pi plus 1 over c. Well, 1 plus 1 over c squared is c squared plus 1 over c squared. And so when you just do the algebra, you get I is equal to c squared, c squared over c squared plus 1 minus sine e to the c pi plus 1 over c, or you get just negative c e to the c pi plus 1 over c squared plus 1. That's our answer. Just doing the algebra. And once we know what I is, we can solve for I by dividing. And 1 plus 1 over c squared is just c squared plus 1 over c squared. So when you bring it to the other side, it becomes c squared over c squared plus 1. And then one of the c's cancel, and we have our answer. So whenever you do a calculation like this, you always want to ask, is this reasonable? Well, if we think about it, cosine alternates. It starts off as positive and then it becomes negative. And so if c is a nice positive number, e to the cx is growing as x gets larger. So if we think about this, it's going to have a larger region where it's negative than it's positive. And so this should be a negative quantity. So before I even do the integration, I have some suspicion of what is going on. So as always, one of the things I really want us to do is start getting comfortable doing calculations. So let's plot x equals from 0. Now, of course, one of the problems is we need to choose what value we want to see. So here's the plot when c equals 0. So if I hit the plus sign over here and expand this out, you can see the value of c. And if you look at this, I see my function when c is equal to 0, just cosine of x, perfectly balanced between positives and negatives. Now let's increase c a little bit and see what happens. So here's the movie. And here's now c equals about 0.56. Especially got my eyesight. And now you can see it's far more pronounced negative than positive. So again, when you're doing calculations, at the end of the day, always ask yourself, is this reasonable? Am I surprised my answer is a negative number? The fact that it is your e to the c pi plus 1 times c divided by c squared plus 1, that's a little bit harder to just look at and see. But just getting a negative value here, that's not so bad. Start the screen share. Okay, so any questions about this bring it over method? So bring it over, as long as you don't have the same coefficient on both sides, you can bring it over and then solve. So if I have I equals crap plus 0.3i, okay, subtract 0.3i from both sides and I get 0.7i equals crap, I equals crap over 0.7. So the bring it over method is extremely powerful. It's really fascinating to look at this example. Did we ever actually integrate cosine of x e to the cx? No, we never actually did the integral. What property did we exploit about cosine that led to this success? what's the source of the miracle? You always want to ask, why did it work? And the better you have the feeling of why things work, the more likely you are to figure out later when to use the method. So why did this work at the end? What allowed us to get I on both sides? So what happens when you take the derivative of cosine once? What do you get? And what happens when you take the derivative again? Yeah, you get negative. So you basically return to where you started up to a constant multiple. That's the source of the miracle. That if you take two derivatives of cosine, you're essentially back to where you started, up to a minus. Now, you could say that I was being a little bit unfair, putting someone on the spot and asking them to choose which to make u and which to make dv. What would have happened if you had done it the other way for this problem? It would have worked just as well. This is one of the few problems where you really can't go wrong. If we had done it the other way, if we had dv equals cosine of x, well then v would have just been sine. And if u was equal to e to the cx, we could take the derivative of that as well. So I believe either way you do this, it's going to work out. It is very rare to have a problem like that, where as long as you do it, you're fine. This is one of the few ones that I think it actually works either way. Yes.
So, like, if you're looking at one initially and say it wouldn't work out either way,
Then you need to use a different technique. So there's other techniques besides integration by commas.
but like, say, like, in this example, you could have used u or v, u or dv for either one.
I believe so.
Like, is the other way, like, you just have to guess and check, or can you like look at it and be like, okay, I think this one's gonna work.
So the real issue is I want to make sure that my integral becomes no worse as I do integration by parts. If I have x squared e to the x, if I make dv x squared dx, then v is going to become x cubed over 3, and I've now increased the degree of the polynomial. I'm making things worse. If I make u x squared and then take the derivative, I now have 2x dx, and I'm making the degree smaller. So, this is not a proof, but it seems to be screaming at you, please, 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 have the x squared as the u, not as the dv. But for this, e to the x and cosine x, these are both nice functions to integrate or to differentiate. And the integral and the derivative of each is basically the same. What's really looking on in the background is cosine and sine are really exponential functions. They're combinations of exponentials with imaginary arguments. And we'll talk about that later. That might be something we'll talk about on Friday. How to relate cosine to exponentials. And that's why it really doesn't matter, because cosine and sine are exponential functions. They just don't look at like that. Let's see. Have you seen like De Moivre's theorem? E to the I theta is cosine theta plus I sine theta. Cosine to the n. So we will talk about trig on Friday probably. Or Monday, maybe Monday's the day. Okay, so we did this. So now we want to go to the method of use substitution. So I actually talked very briefly about this earlier. And the idea is if I give you f of g of x prime, this is f prime of g of x times g prime of x. So if I ask you, can you give me a function whose derivative is the derivative of f of x, of f of g of x? What function has derivative of f of g of x? So what? F of g of x. So if I integrate both sides, the left-hand side is very easy. It's just f of g of x. And so what we often do is we write this as the integral of f of u du, where u is g of x, du dx is g prime of x, so du is g prime of x dx. We have to be a little bit careful about the range of integration. So it's important that when u equals g of x, we need this to be a increasing or decreasing function. So why is this important? So let me first. So increasing just means it always gets larger as you go to the right and smaller to the left. Decreasing means you always get smaller to the right and larger to the left. So let's look at the integral from -2 to 2. 1 over 1 plus x squared dx. So let's try u equals x squared. So what would du be? Yes. I want to do that example. So let's take u to be x squared. What would du be? By 2x dx. So dx would be du over 2x or du over 2 square roots of u. If x goes from -2 to 2, then what does u go from? When x is -2, what is u? 4. And when x is 2, what is u equal to? 4. So our integral equals, and I'll put this in quotes because it's not, the integral u goes from 4 to 4 of 1 over 1 plus u squared, 1 over 2 square roots of u to u. But what does that integral equal? 0. I'm integrating from 4 to 4. This is absurd. So this is not a one-to-one transformation. If you look at what's going on, if you look at y equals g of x, it first decreases and then it increases. If you give me a value of y, I see there are 2 different values of x that go with it. This is bad. What I want is I want something like this. Some kind of curve like this. So you give me a value here, there's one and only one value of x that goes with it. And so I need my function to be increasing or decreasing. So really what I need is g prime of x should be greater than 0 or g prime of x should be less than 0 on the integral. Because the first derivative tells you whether or not you're increasing or decreasing. So if I want to do a change of variables like this is a good way to do it. Now you said, what if we make u equal 1 plus x squared? So we could absolutely try that. The problem is when we do that, it's going to lead to a difficult integral. And this is not an integral that we can solve nicely. The best way to do this is to write that this is just twice the integral from 0 to 2 of 1 over 1 plus x squared dx. And now, if we do something like that, we're only using half the parabola. And now it's going to be strictly increasing. And now we can use techniques like this. Unfortunately, this integral is actually a painful integral. It's not u squared, sorry, it's just. Technically, what I wrote is not wrong. Why is what I wrote not wrong? It shouldn't have the square there. It should just be 1 over 1 plus u, not 1 over 1 plus u squared. But why is it not wrong for me to put a square there? Because that also equals 0. I'm integrating from -4 to 4. I'm sorry, I'm integrating from 4 to 4. It doesn't matter what I put in. The integral is going to be 0. I can have a typo and write u squared rather than u. It's not going to make any difference. But now if I try something like this, now I'd be integrating from 0 to 4 of 1 over 1 plus u times 1 over 2 root u. And this is just not an easy integral to do. But we've seen how to do 1 over 1 plus x squared. One was to use the arctangent. Another was to do change of variables, letting x be tangent to theta. And we'll talk more about that later. So I just went and found 2 different websites with a bunch of integrals. So I put down 9 different integrals. Are there any preferences for ones to do that you would like to see? Let's do as many of them as we can in the amount of time we have. First one. So I'll copy that over here. Let's find this integral. We need to figure out what kind of change of variables to do. So what would you try to guess for the u substitution? What would you try for u? Yes. Yeah, let's try u, and let's make this go from 0 to 8. So let's try u equals 3x plus 4. X goes from 0 to 8. So what does u go from? When x is 0, what is u? 4. And when x is 8, what is u? 28. And so this would be the integral from 4 to 28 of u to the 1/2. Now I've got to be very careful. What is du? So if u equals 3x plus 4, what's du dx? It's just 3. So that means du is 3 dx, or dx is 1/3 du. Why am I writing dx as 1/3 du? Well, because I have square root of 3x plus 4 times dx. I have to substitute for both of these parts. The square root of 3x plus 4, that's just u to the 1/2. The dx, that's just 1/3 du. And now I'll say, okay, well, that's 1/3. The integral u goes from 4 to 28 of u to the 1/2 du. Right. What function has derivative u to the 1/2? U to the 3/2. And then what constant do I have to have in front of the u to the 3/2? 2/3, perfect. There is no excuse in this class for getting an antiderivative wrong. Why is there no excuse? You can always check. There is plenty of excuses for not being able to get an antiderivative. That's fine. Well, if it's not fine, that means I'm failing as a professor, but it's okay if you can't find the antiderivative. But it's not okay if you have the wrong antiderivative, because we can always check. We're very fortunate we got it. And then we just evaluate this at 4 and 28. So it would just be 2/9 times 28 to the 3/2 minus 4 to the 3/2. Do I actually care what that number is? No. I just care about how we reach it. And so this would be a canonical example of use substitution. And so here, my function g of x is 3x plus 4. G prime of x is 3, which is always greater than 0, so it's increasing. So what we're doing is legitimate. Okay. Any questions on this example? Okay.
So
So we have two things here. We have the integrand, the square root of 3x plus 4, and we have the dx. And we have to figure out how do we switch each one? How do we change? If u is 3x plus 4, this is why I always write the du dx. Now, the books normally just go to straight to du equals 3 dx. I like to go du dx is equal to 3. So that means du is 3 dx. So every time I have a small little increment dx, the du is 3 times that. Which makes sense. U is equal to 3x plus 4. If you increase x by 1, u increases by 3. So think of this as a conversion factor. And so I need to figure out what is dx. Well, dx then is just 1/3 du. So when I have my dx here, I need to solve for dx in terms of du and u. And now I can just substitute in for each piece. But I can't just replace the dx with du because dx is not the same as du.
So it's not like just notation.
It's not just notation. So let's do another problem, and hopefully the more problems we do, the next thought. Any problems look particularly interesting to do. Bottom right. Oh yeah, that looks interesting. So I have deliberately not thought about how to do any of these problems. It's not because I don't care about you enough to prepare a class, but I think it's actually better not to have thought about this and to just do the thought process live with you. Or at least that's the story I'm going to stick with. When you look at this, it looks a little nasty. We've got a square root of a square root. So we need to think of something to try. Yes. So, I mean, it's just rewriting it. It's the same thing. This is the integral from 0 to 9 of 4 minus x to the 1/2 to the 1/2 dx. We can write it like that. That's perfectly fine. Yes. So we can try that. We can try that. So let's try u equals 4 minus x to the 1/2. Then as x goes from 0 to 9, what does u go from? So when x is 0, what would u be? 4. And when x is 9, what would u be? 1. Okay, so it looks like this is a perfectly fine range. If u is 4 minus x to 1/2, du dx, what is du dx going to be? So negative 1/2 x to the negative 1/2. And that's always going to be negative in this range. Okay, that's good. Now we need to solve for dx. So dx is going to equal so du is negative 1/2 x to the negative 1/2 dx. So dx is negative 2 x to the 1/2 du. Right? Is everybody comfortable with that? I just multiply both sides by 2x to the 1/2. The problem is I can't have 2x to the 1/2 du. I'm getting rid of x and replacing x's with u's. So I have to replace x to the 1/2 with u. So before we had u equals 4 minus x to the 1/2. Oh, life is good. I'm trying to solve for x to the 1/2 in terms of u. Yeah, just move it over to the other side and get x to the 1/2 equals 4 minus u. there's no need to try to figure out, well, let's square it and solve for x. We just need to get x to the 1/2. I can get x to the 1/2 easily. So that means, back to red, that dx is going to be -2 4 minus u du. So the integral is going to be the integral, u goes from 4 to 1, 4 minus x to the 1/2. What is 4 minus x to the 1/2? I need to write things in terms of u. What is 4 minus x to the 1/2? To the 1/2. How would you write that in terms of u? Sorry? Well, u is 4 minus x to the 1/2. It's just u to the 1/2. Right? 4 minus x to the 1/2, that's just u. That's the first part. What about the dx? What would that be? That would just be -2 4 minus u du. So this is just going to be -2 integral u goes from 4 to 1 of u to the 1/2 4 minus u du. There's a couple of ways to do it. One of the things I want to do now is, we're normally not used to integrating from 4 to 1. We normally integrate from the lower to the upper. It costs you a minus sign to flip the order of integration. We have a minus sign right outside. So this is the same as just 2, the integral u goes from 1 to 4 of u to the 1/2 4 minus u du. How do you evaluate this integral? What should we do? Distribute. And who teaches us to distribute? Our favorite New England transcendentalist, Thoreau. Right? So this is now just going to be twice. We'll have the integral u goes from 1 to 4 of u to the 1/2 du. I'm sorry, 4 u to the 1/2 du minus the integral u goes from 1 to 4 of u to the 3/2 du. So the first one, what function has derivative u to the 1/2? It's going to be u to the 3/2, and we'll have a 2/3 there, evaluated at 1 and 4, minus u to the 5/2, we'll have 2/5 at 1 and 4. Right? And now we just have to substitute in. And so then we just do some algebra. So it's going to be 2. And then the first one, we're going to have 8/3. When u equals 4, 4 to the 3/2 is going to be 8. So when you take the square root of 4, you get 2, and then when you cube it, you get 8. So the 8/3, 8 minus, and then when we have 1, it's just 1. And it'll be minus 2/5. And then when I put in 4, 4 to the 5/2 is the same as 2 to the 5th, which is 32. So it'll be 32 minus 1. And so that should be the answer. And so that is how we would do the use substitution. So choosing u to be 4 minus x to the 1/2 was an excellent choice. If that hadn't worked, what might you try? I'd probably try next, if that didn't work, maybe u equals the square root of x. That'd be my next thing to try. Okay, any questions about this point? Again, I hope this gives you another place of seeing the dx du conversion. It really is not just changing x to u, it's how is dx related to du. We get that by looking at du dx. Okay, so let's go back. We've got plenty of other problems. I'll choose. So the first thing, of course, when I see this is I would immediately pull out the 3. And it's just the integral of 1 over x natural log of x dx. And I'll do it as an indefinite integral this time, not a definite integral. So I've got to figure out what to choose for u. Any thoughts about what might be nice? Well, if I take x ln of x, the whole thing is my u. But it's a little bit much to make it to be the u. ln of x. You can view this as it's the integral of 1 over natural log of x, 1 over x dx. What's the derivative of natural log of x? 1 over x dx. By writing it like this, I can see, oh, okay. Probably a good choice is to make u equals natural log of x, because then the du is going to be perfectly positioned. You know, again, this is the advantage of having done this for deep in my 4th decade of doing problems like this. So when you've done it for this long, you should be able to just look at these and see this is a good thing to do. It's experience. So let's try u equals natural log of x. Du dx would be 1 over x, which is going to, as long as we're integrating over a positive range or negative range, increasing or decreasing things are good. So du is 1 over x dx. Is there any need to isolate what dx is? No, I've got 1 over x dx. So there's no need to isolate. So our integral is now going to be the integral of 1 over u du. And what's the integral of 1 over u du? It's just ln of, no, it's not ln of x. You're close. What's the integral of 1 over u? ln of u. Yeah, but I was actually just about to say there's always these plus c's going on. So it's ln of u, and then we can for this one because it's an indefinite integral, any constant would work. But what is u equal? Right, so this is really the natural log of the natural log of x. Let's see. And that would be the answer. And so, you're right. The 3 is along for the right. Does the 3 have to hit the c? No, because the c is an arbitrary constant. Any questions on this one? So the whole point is to just find good things to try. The more problems you do, the easier it is to get a sense. We have time, I think, for one more. And again, we can do more of these when we do the review debate. Sure, which one? Sure. And the top one is actually very nice. Whoever wrote the top one was thinking kindly of people. So when you see x cubed plus 3x, what's the derivative of x cubed plus 3x? 3x squared plus 3. What's, again, 4 decades, right? So if we take u to be x cubed plus 3x, du dx is going to be 3x squared plus 3 is 3x squared plus 1. So du is going to be 3x squared plus 1 dx, or 1/3 du is x squared plus 1 dx. So the integral is going to be the integral of 1 over u 1/3 du. And what's the integral of 1 over u? Yeah, it hasn't changed from last time. It's still holding constant, plus c. But now, what is u in this problem? X cubed plus c. So now we get 1/3 the natural log of x cubed plus 3x. Let's see. And if you really wanted to, you could write this as 1/3 the natural log of x plus the natural log of x squared plus 3 plus c. If you wanted to just factor that a little bit. There's really no need, but okay. We might have time to do one more. Let's do this one. So here's another one. So we have to figure out, what do you think u is? If you look at it, I have an x plus 3 and I have an x minus 1 to the 5. What might be a good choice of u? Yeah, so let's try u equals x minus 1. What would du dx be? Oh, life is good, right? Du is dx. That's the simplest possible conversion I can have. Now, what is x plus 3? I need to convert x plus 3. Well, if u equals x minus 1, then what does x equal in terms of u? U plus 1. So x plus 3 is just going to be u plus 4. And the integral is going to be the integral of u plus 4 times u to the 5th. Right. What should we do now? Distribute. And which New England transcendentalist do we think? Deveau. And so if we distribute, this is now going to just be the integral of u to the 6th du plus 4 times the integral of u to the 5th du. So it'll just be 1/7 u to the 7th plus 4/6. I know I could reduce it. U to the 6th plus c. Very, very briefly, there is kind of another way to do this. It's mostly the same. What I could do is, if I start off with this is my integral, I could write x plus 3 as x minus 1 plus 4. And it's okay, if this is a little confusing, don't worry. Then my integral would be the same as x minus 1 plus 4 times x minus 1 to the 5th dx, which is the integral of x minus 1 to the 6th dx plus 4 times the integral of x minus 1 to the 5th dx, which would then just be x minus 1 to the 7th over 7 plus 4/6 x minus 1 to the 6th plus c. So it's a very similar way to do it, just rewriting things in a nice way. On the last line over here, we really should now replace u with x. So this would be 1/7 u is x minus 1 to the 7th, plus now simplify to 2/3 x minus 1 to the 6th. All right, so this is use substitution. We will do more of these problems later. Have a great rest of the day.